reporter for our vapor compression refrigeration cycle experiment. So first off, we're going to explain the coefficient of performance again, even though we've heard it 4 times today. Coefficient of performance is defined as the energy sought divided by the energy that costs, like what you want to move from one place and how much work it takes. And it's defined as beta is equal to QL over the work of the compressor in our case. And that's the heat transferred from the refrigerated space and the work input from the compressor. So here's a refrigeration cycle on a pH diagram. I'll go through it. So right here we have a pH diagram of R134A, our refrigerant in our case, and our state 1 hypothetical is there. It's on the saturated vapor side of the vapor dome, as is given in the ideal case. From state 1, we move to state 2 through a compression cycle through a compressor. And from state 2, you see it's in the superheat region. We then condense that down to a saturated liquid on the saturated liquid side of the vapor dome for state 3. Going from state 3 to state 4, we go through our thermostatic expansion valve, which is isenthalpic. And going from state 4 back to state 1, we run it through the evaporator. In the ideal case for our calculations, we go from state 1 to state 2S, which is an isentropic process. It just makes our calculations a lot simpler, but we also understand that there's no way to have an isentropic compression cycle. And we have a thermostatic expansion valve, as I mentioned, from state 3 to state 4. We run it through one of these. So the sensing bulb over there is placed on the outlet of the evaporator, and that boils a refrigerant inside of the bulb, and it creates pressure in the capillary tube, which then moves the diaphragm on the power head, and it controls how much refrigerant is let into the evaporator. So your refrigerant comes in here, and it goes out here, and the goal of this device is to maintain a constant superheat through the evaporator, so we actually evaporate off all of the liquid before we run it back through the compressor, because liquid in a compressor is bad news. So exercise 1, our goal was to determine the power consumed, the produced heat, and the coefficient of performance. From our software, we got our power consumed by the compressor of 47.9 watts. Condenser water inlet temp is 23.9 degrees Celsius, and the condenser water outlet temp of 28 degrees Celsius. Using a flow rate of 5 liters a minute, we get a flow rate of 0.085 kilograms per second. Our produced heat equation, m dot Cp Tw out minus Tw in, we get a value of 1456.73 watts using a specific heat of 4180 joules per kilogram Kelvin. And this yields us a coefficient of performance of about 2.985. And our calculated coefficient of performance here is less than that of the ideal Carnot cycle, as it's supposed to be. In factors that affect our coefficient of performance is the temperature range between the condensation and evaporation portions of our cycle. A larger difference yields a very low coefficient of performance, and a small difference yields a high coefficient of performance. Also, the refrigerant that you use also can severely affect your coefficient of performance. R134A is far less efficient than ammonia. They evaporate and condense at different temperatures and pressures and so on. They actually use ammonia on the International Space Station because it works a lot better up there than R134A. So exercise 2, we ran it with the different flow rates of water through the evaporator, and we came to, this is the ideal case of our cycle, what we hope it to be like for simplifications of calculations. Just see state 1 over here on the saturated liquid, or saturated vapor side of the dome, state 2 out here in the superheat region, state 3 on the saturated liquid side of the dome, state 4 isenthalpic, state 3 through the expansion valve, and then back through the evaporator back to state 1. So our experiment yielded this. So we see that state 1 is in the superheat region, unlike the ideal where it should be back over here on the vapor dome. State 2 also in the superheat region, assuming an isentropic compression. And state 2 moves to state 3. State 3 is actually slightly subcooled. That's over here in the saturated liquid side. And state 4, again, in the vapor dome like it should be. So the ideal case is assume that state 1 is saturated vapor, state 2 is in superheat, state 3 is a saturated liquid, and state 4 falls in our vapor dome. It also assumes a steady state operation of our cycle. In the experimental case, we see that our state 1 is in the superheat region. This is due to the settings on the thermostatic expansion valve. It's not, all of it's not boiling off, right? We still have some superheated vapor at a low pressure. State 3 is in the saturated liquid side of the superheat region, so it's subcooled, so it's very much all liquid going back through the expansion valve. And these could be due to the non-steady state operation of the cycle. Another note here, the data given to us in the steam tables in the back of the lab manual was quite a bit different than the data given in the back of the thermo textbook. Like at 0 degrees C, our enthalpy according to the lab manual was 50.2 kilojoules per kilogram, and in the back of the thermo book, it's like 200 kilojoules per kilogram. So I went with what I was comfortable with, which was back of the thermo textbook, and pulled it all into Excel and made these plots. So I referenced thermal book and how thermostatic expansion valves work. Are there any questions?